the birth of the universe, and the first steps towards death. The universe in which we live is not eternal. It has a beginning, and as we now understand, it is also moving inexorably towards an inevitable end. To fully grasp the concept of the death of the universe, we must first return to its birth. The beginning of the universe is defined by an event known as the Big Bang, which took place around 13.8 billion years ago. At the time of the Big Bang, space, time, matter, and energy were concentrated in an incredibly dense and hot spot, often referred to as a singularity. It's hard to imagine, but this singularity contained all the ingredients necessary for the creation of everything we see in the universe today. Every star, every planet, every galaxy, and even you. From this singularity, the universe began to expand at an astonishing speed, creating both space and time. This rapid expansion is known as cosmic inflation, a concept introduced by the physicist Alan Guth in the 1970s. According to the theory of inflation, the universe expanded faster than light in the first second after the Big Bang. To give you an idea of scale, in less than a second, the universe grew from a size smaller than an atom to a size roughly equivalent to a grapefruit. This phase of inflation smoothed out the structure of the universe and led to the formation of the large-scale structures that we observe today, such as galaxies and galaxy clusters. As the universe expanded and cooled, particles began to form. In the first few moments, elementary particles such as quarks, leptons, and gluons filled the universe. Quarks combined to form protons and neutrons, and shortly afterwards, protons and neutrons combined to form the nuclei of simple atoms, mainly hydrogen and helium. This process is known as nucleosynthesis and took place within the first 3 minutes after the Big Bang. About 380,000 years after the Big Bang, the universe cooled down enough for electrons to combine with these nuclei and form neutral atoms. This period is known as recombination, and it is significant because it allowed light to move freely through the universe for the first time. The light from this era still exists today as cosmic background radiation, CMB, a faint glow that fills the universe and shows a picture of the universe when it was only a few 100,000 years old. Fast forward billions of years and the universe has changed dramatically. Stars have formed from massive gas clouds, galaxies have merged, and black holes have appeared at the center of most galaxies. Today's universe is much more structured and complex than when he was a child. But even as the universe was maturing, it was already beginning its slow journey towards death. One of the most important discoveries in modern cosmology was made in the 1920s, when the astronomer Edwin Hubble observed that galaxies were moving away from us. This observation led to the realization that the universe is still expanding. Hubble's work also introduced the concept of redshift, the phenomenon whereby the light from distant galaxies shifts towards the red end of the spectrum as these galaxies move away from us. This red shift is an important indication of the expansion of the universe. But here comes the surprise. The universe is not only expanding, it is expanding at an accelerated rate. This was discovered in the late 90s of the 19th century when two independent teams of scientists studying distant supernovae found that galaxies are moving away from us faster today than in the past. This acceleration is driven by a mysterious force known as dark energy, which we will discuss in more detail in the next chapter. For now, let's concentrate on what we have learned so far. The universe had a beginning, and it is expanding. But this expansion cannot go on forever. Eventually, it will lead to one of several possible fates for the universe. Will it keep expanding, getting colder and darker until there is no energy left? Will it collapse one day, which is known as the Big Crunch? Or is something completely different in store for the cosmos? In the following chapters, we will explore the various theories and ideas about the future of the universe. We will look at the role of dark energy, the fate of stars and galaxies, and the mysterious nature of black holes. But first, let's take a closer look at the force that seems to control the fate of the universe: dark energy. Dark energy, the driving force behind the accelerating universe. At the end of the 1990s, astronomers made a discovery that would change our understanding of the future of the universe. The expansion of the universe is accelerating. Up to this point, most scientists believed that the expansion of the universe, which was set in motion by the Big Bang, would gradually slow down, as the gravitational pull of all matter would have to slow the universe down. It was even thought that the expansion could one day stop altogether and reverse, leading to a so-called Big Crunch, in which the universe collapses back into a singularity. But the discovery of this acceleration threw these theories out the window. The two teams that made this groundbreaking discovery were studying distant supernovae, specifically type Ia supernovae, the explosions of dying stars. These supernovae are known as standard candles in astronomy because their intrinsic brightness is well understood, and they can therefore be used to measure huge distances. By observing the light from these supernovae, scientists can determine how far away they are and how fast the galaxies in which they are located are moving away from us. What they found was shocking. The supernovae were further away than expected, suggesting that the expansion of the universe is not just continuing, it is accelerating. Something was driving the galaxies apart, and this something was not just the opposite of gravity. It was a force that accounted for about 70% of the total energy of the universe, but it was invisible and only detectable through its effects on the expansion of space. This force became known as dark energy. But what is dark energy? The short answer is, we don't know exactly. There are several theories, but none can fully explain the nature of dark energy. One possibility is that dark energy is related to what Einstein called the cosmological constant, a term he added to his equations of general relativity to describe a static universe. When it was discovered that the universe was expanding, Einstein famously described the cosmological constant as his greatest mistake. But it turns out that this mistake was perhaps correct after all, just in a different context. Instead of keeping the universe static, the cosmological constant could be responsible for the accelerated expansion of the universe. Another theory suggests that dark energy could be a property of space itself. According to quantum field theory, even empty space is not really empty. It is filled with virtual particles that constantly appear and disappear again, a phenomenon known as quantum fluctuations. These fluctuations could give space a kind of intrinsic energy that drives the acceleration of the expansion of the universe. There is also a more exotic idea, that dark energy is not constant, but changes over time. This concept is known as quintessence, where dark energy is seen as a dynamic field that evolves with the expansion of the universe. If dark energy is indeed variable, this could lead to different scenarios for the fate of the universe. For example, dark energy, if it gets stronger over time, could eventually lead to a scenario known as the Big Rip, in which the expansion of the universe accelerates so much that galaxies, stars, planets, and even atoms are torn apart. What we know so far, however, is that dark energy is driving the expansion of the universe, and that this expansion is accelerating. This leads us to one of the most widely accepted scenarios for the end of the universe, the Big Freeze. In the Big Freeze scenario, the universe continues to expand indefinitely. As it expands, the galaxies move further and further apart until they are no longer visible. Over billions and trillions of years, the stars will burn up their nuclear fuel and go out, leaving behind white dwarfs, neutron stars, and black holes. The universe will get colder as it expands, and the formation of new stars will slow down until it eventually stops altogether. The remaining galaxies will remain isolated in the vast, empty space. As the universe cools, it will also reach a state known as heat death, in which all matter and energy are evenly distributed and no more thermodynamic processes can take place. In this state, the universe will have reached maximum entropy. This means that no more work can be done, no more energy can be used, and no more structures can be formed. Time may continue to exist, but there will no longer be any events to mark its course. The universe will be a cold, dark, and empty place. This slow, inevitable death may seem bleak, but it is not the only possible fate for the universe. While the Big Freeze is one of the most widely accepted scenarios, there are other possibilities, especially if the dark energy behaves in ways we don't yet understand. In the Big Rip scenario, dark energy not only continues to drive the expansion of the universe, it becomes stronger and stronger over time. As the dark energy becomes stronger, the rate of expansion accelerates exponentially until it eventually tears apart not only galaxies, but also stars, planets, and even atoms. This scenario describes a universe that is literally torn apart by the force of its own expansion. The decisive difference between the Big Freeze and the Big Rip lies in the nature of the dark energy. If the dark energy remains constant, as suggested by the cosmological constant, the universe will probably experience the Big Freeze. But if the dark energy becomes stronger over time, this could lead to a Big Rip. Current observations suggest that dark energy is constant, but this could change with future discoveries. In the Big Rip scenario, the time frame for the end of the universe would be much shorter than in the Big Freeze. Some estimates assume that the Big Rip could occur in just 20 to 30 billion years. Although this seems like a long time from a human perspective, it is relatively short on cosmological timescales. Could dark energy be reversed? A final possibility is that dark energy could somehow be reversed or even canceled out in the distant future. Some physicists have speculated that dark energy is not a permanent feature of the universe, but a temporary phase. If the dark energy were to weaken or disappear, the expansion of the universe could slow down and eventually stop. This could lead to a scenario known as the Big Crunch, in which the universe reverses its expansion and collapses under its own gravity, eventually ending in a hot, dense state similar to the conditions of the Big Bang. While the Big Crunch is a less likely outcome based on current observations, it remains a theoretical possibility. If the universe were to collapse, this could even trigger a new Big Bang, which would lead to a cyclical universe that goes through infinite cycles of expansion and contraction. This idea, known as the cyclical universe model, has been studied by cosmologists who attempt to unite the beginning and end of the universe in a continuous cycle. In this chapter, we have explored the mysterious nature of dark energy and its role in shaping the future of the universe. Whether the universe ends in a cold, dark freeze or a violent rip, dark energy is the driving force behind its fate. But what about the objects that remain in the universe? The stars, planets, and black holes? In the next chapter, we will examine the fate of the stars and the remnants they leave behind as the universe nears its ultimate end. The life and death of the stars, the shining giants of the universe. Stars are the engines of the universe. For billions of years, they have provided light, heat, and the raw materials necessary for the formation of planets, life, and galaxies. But stars, like all things, have a lifespan. They form from huge clouds of gas and dust, burn up their nuclear fuel, and eventually die, leaving behind remnants such as white dwarfs, neutron stars, or black holes. To understand the future of the universe, we need to study the life cycle of stars and the cosmic consequences of their death. Stars form in massive molecular clouds, regions in space where gas and dust accumulate in sufficient quantities to collapse under their own gravity. When the cloud collapses, it begins to heat up until temperatures high enough to trigger nuclear fusion are reached. This fusion process is what drives stars and makes them shine for billions of years. In the core of a young star, hydrogen atoms fuse to form helium, releasing energy in the form of light and heat. This energy creates an outward pressure that balances the inward pull of gravity and allows the star to maintain its size and stability. The balance between these forces keeps a star stable for most of its life, a phase known as the main sequence. How long a star remains in the main sequence depends on its mass. Low-mass stars, like our Sun, can burn their hydrogen fuel for billions of years. Larger stars, on the other hand, use up their fuel much more quickly, sometimes in just a few million years. The more massive the star, the shorter its lifespan. Eventually, a star will use up the hydrogen in its core. For a star like our Sun, this marks the beginning of the end. Once the hydrogen fuel is exhausted, the core contracts, while the outer layers of the star expand, transforming it into a red giant. In this phase, the star becomes much larger and cooler on the surface, while the core continues to shrink and heat up. As soon as the core is hot enough, helium fusion begins, in which helium is converted into carbon and oxygen. However, this phase is much shorter than the hydrogen-burning phase. As soon as the helium in the core is used up, the star no longer has enough pressure to support its outer layers. The outer layers are ejected into space and form a planetary nebula, while the core remains as a white dwarf. White dwarfs are incredibly dense objects, about the size of the Earth, but with a mass similar to that of the Sun. They no longer undergo nuclear fusion, which is why they gradually cool down and fade over billions of years. In the distant future, white dwarfs will become black dwarfs, cold, dark remnants of stars that no longer emit light or heat. This process takes trillions of years, so black dwarfs do not yet exist, but they will play a key role in the final stages of the evolution of the universe. While low-mass stars like the Sun end their lives as white dwarfs, more massive stars suffer a more violent fate. When a massive star has used up its hydrogen fuel, it also becomes a red giant. But instead of gently shedding its outer layers, it undergoes a cataclysmic explosion known as a supernova. A supernova occurs when the core of a massive star collapses under its own gravity and triggers an uncontrolled fusion reaction that blows the star apart. The outer layers of the star are ejected into space, while the core is compressed into an incredibly dense object. Depending on the mass of the star's core, this remnant becomes either a neutron star or a black hole. Neutron stars are among the densest objects in the universe, with a mass greater than that of the Sun, but compressed into a sphere only a few kilometers across. Neutron stars consist almost entirely of neutrons, which are produced when protons and electrons are squeezed together during the collapse of the star. These stars can rotate rapidly and emit beams of radiation from their magnetic poles, a phenomenon known as pulsars. For the most massive stars, the core collapses even further and forms a black hole. A black hole is a region of space where gravity is so strong that not even light can escape. The boundary around a black hole is called the event horizon, beyond which nothing can return. Black holes are among the most mysterious and fascinating objects in the universe, and they play a crucial role in its long-term evolution, as we will explore later. Our Sun is a relatively small star with a total lifetime of around 10 billion years. It is currently in the middle of its life, in the stable hydrogen combustion phase of the main series. In about 5 billion years, the Sun will begin to use up the hydrogen in its core, marking the beginning of the red giant phase. As the Sun expands into a red giant, its outer layers will engulf the inner planets, including Mercury, Venus, and possibly Earth. Life on Earth will have long since died out by this time, as the increasing heat of the expanding Sun will have made the planet uninhabitable. Eventually, the Sun will shed its outer layers and form a planetary nebula, while its core will become a white dwarf. The remaining white dwarf will be incredibly dense, with a mass of about half that of the Sun, compressed to the size of the Earth. Over the course of billions of years, it will cool and fade, eventually becoming a black dwarf. At that time, the planets in the outer solar system, Jupiter, Saturn, Uranus, and Neptune, will continue to orbit the white dwarf, but the solar system will be a cold, dark, and lifeless place. As the universe continues to expand and dark energy accelerates the separation of galaxies, the remaining stars will use up their nuclear fuel and die. In the distant future, star formation will slow down and eventually stop altogether. This will mark the beginning of the degenerate era, a time when only stellar remnants, white dwarfs, neutron stars, and black holes remain. As the universe cools and darkens, these remnants will continue to radiate their remaining energy. White dwarfs will gradually cool down and become black dwarfs, and neutron stars and black holes will last for trillions of years. In this era, the universe will be dominated by these faint, dead stars, with no new stars emerging to replace them. But even in the degenerate era, black holes will play an important role. Over incredibly long periods of time, black holes will continue to devour matter and merge with each other, becoming ever larger and more massive. Eventually, all the matter in the universe could be swallowed up by black holes, leaving only these gravitational giants to shape the universe. But even black holes are not eternal. In the next chapter, we will explore what happens to black holes over time and how their final evaporation will contribute to the slow decline of the universe. The endgame of the black holes, giants of the cosmic graveyard. As the stars fade and the universe drifts into the distant future, black holes become the dominant structures in the cosmos. These gravitational giants, formed by the collapse of massive stars and the merging of galaxies, will reign in the degenerate era, a time when the stars no longer shine and the universe is a cold, dark place. But even black holes are not immortal. Over unimaginable periods of time, they too will eventually fade away and contribute to the final stage of the universe's slow decline. Let's explore the role of black holes in the endgame of the cosmos and how their fate is closely linked to the ultimate end of the universe. What are black holes? To truly appreciate the role of black holes in the fate of the universe, we need to understand what they are and how they behave. A black hole is a region of space-time in which gravity is so strong that nothing, not even light, can escape. The boundary around a black hole, known as the event horizon, marks the point of no return. As soon as an object crosses this boundary, it is doomed to be drawn into the singularity of the black hole, a point of infinite density at which the laws of physics, as we know them, break down. Black holes come in different sizes, from stellar black holes, which are formed by the collapse of massive stars, to supermassive black holes, which are located in the centers of galaxies and have a mass of millions or even billions of solar masses. The origin of supermassive black holes is one of the great mysteries of astrophysics, but they are thought to have formed early in the history of the universe, either through the merging of smaller black holes or through the direct collapse of massive gas clouds. Once a black hole has formed, it can grow by sucking in matter, such as gas, stars, or even other black holes. The more a black hole consumes, the more massive it becomes. But as we will see, black holes also lose mass over time through a process known as Hawking radiation. In 1974, physicist Stephen Hawking made a groundbreaking discovery. Black holes are not completely black. Through a quantum mechanical process, black holes can emit radiation, which is now known as Hawking radiation. This phenomenon occurs near the event horizon of a black hole, where quantum fluctuations lead to the spontaneous creation of pairs of virtual particles. Normally, these pairs of particles annihilate each other almost instantly. But if one of the particles falls into the black hole while the other escapes, the black hole loses a tiny amount of its mass. Over time, this causes the black hole to shrink and eventually evaporate completely. The process of Hawking radiation is incredibly slow. A typical stellar black hole would take far longer than the current age of the universe to completely evaporate. The larger the black hole, the slower it loses mass. In the case of supermassive black holes, the process is even more protracted and extends over unimaginable periods of time, on the order of trillions or even quintillions of years. As the universe enters the era of black holes will be the last significant objects in the cosmos. They will continue to grow by soaking up all the remaining matter in the universe, but eventually they too will start to lose mass due to Hawking radiation. Over time, the universe becomes colder and emptier, while the black holes slowly evaporate and release their energy back into space as radiation. One of the biggest mysteries in connection with black holes is the so-called information paradox. According to the principles of quantum mechanics, information about a physical system can never be destroyed. This means that in theory, even if an object is pulled into a black hole, the information about its state, its position, momentum, and other properties should be preserved in some way. However, black holes seem to violate this principle. As soon as an object crosses the event horizon, all information about it seems to be lost. If the black hole finally evaporates, the information trapped in it would be gone forever, which obviously violates the rules of quantum mechanics. This paradox has preoccupied physicists for decades. Some theories suggest that information may be encoded on the black hole's event horizon in a kind of hologram, in a way that preserves it even when the black hole evaporates. This idea is known as the holographic principle. According to this theory, all information about the objects that fall into a black hole is stored on the two-dimensional surface of the event horizon, while the three-dimensional interior is only a projection of this information. Another possibility is that the information is somehow preserved in the Hawking radiation emitted by the black hole, although this idea is controversial. Solving the information paradox of black holes is one of the greatest challenges in theoretical physics and could lead to a deeper understanding of both quantum mechanics and general relativity. As the universe continues to expand and dark energy drives galaxies further and further apart, black holes will be the last significant structures. In the distant future, trillions of years from now, the last stars will be extinguished and the universe will enter the degenerate era. During this time, black holes will continue to dominate, but they too will eventually come to an end. As black holes lose mass due to Hawking radiation, they will shrink and become hotter. In their final moments, they will emit a burst of radiation as they release their final mass. For stellar black holes, this process will take trillions of years, but for supermassive black holes, the time frame is much longer. As soon as the last black hole has evaporated, the universe will enter its final phase, the dark era. After the last black hole has evaporated, the universe will be a cold, empty place. Without stars, planets, or black holes, the universe will only be filled with weak radiation and subatomic particles such as electrons and neutrinos. This marks the beginning of the dark era, a time when the universe has reached a state of maximum entropy and no more energy is available to drive processes. In this final state, the universe will have essentially used up all usable energy. All matter will have decayed, and the remaining radiation will be so diffuse that it will be practically undetectable. The universe will continue to expand, but without structures or energy sources, time itself could lose its significance. This is the ultimate fate predicted by the Big Freeze scenario, in which the universe sinks into darkness and silence. Black holes play a decisive role in the development of time itself. As we discussed in Chapter 2, the arrow of time is closely linked to the concept of entropy, which always increases over time. Black holes are objects of extreme entropy. When matter is drawn into a black hole, the total entropy of the universe increases. This means that black holes are an important driver of the cosmic progression towards heat death. As soon as the last black hole has evaporated, the universe will have reached its maximum possible entropy. In this state, without energy gradients and without processes that drive change, time could lose its meaning. The flow of time, as we understand it, is marked by the occurrence of events and the exchange of energy. In the dark era, with no events and no energy, time could become an empty concept that runs on indefinitely, but with no way to measure its progression. In this chapter, we have examined the role of black holes in the endgame of the universe. From their formation to their final evaporation, black holes are the last beacons of activity in the universe. But when even these giants fade, the universe enters its final and darkest phase, a time when nothing remains but the faintest echoes of a once pulsating cosmos. In the next chapter, we turn to the possibility of new beginnings. Could the death of our universe herald the beginning of something new? We will explore the fascinating idea of the multiverse and investigate whether the end of our universe might just be the beginning of a new one. The multiverse. Is our universe one of many? As we ponder the ultimate fate of our universe, a cold, dark, and lifeless nothingness, the question arises, is this the end of everything? Or could it be just one chapter in a much larger cosmic story? This is where the concept of the multiverse comes into play, one of the most speculative and fascinating ideas in modern physics. According to the multiverse hypothesis, our universe may not be the only one. In fact, there could be an infinite number of universes, each with its own physical laws, constants, and outcomes. If this is true, the death of our universe might not be the end, but merely the end point in a multiverse full of other realities. The idea of the multiverse has its roots in several different areas of theoretical physics, including quantum mechanics, cosmic inflation, and string theory. Although these areas are often considered separately, they each offer insights into a bigger picture in which our universe is just one of many. One of the earliest multiverse theories stems from research into cosmic inflation. As we discussed in earlier chapters, the universe underwent a rapid expansion in the first moments after the Big Bang. This inflationary phase smoothed out the universe and gave rise to the structures we see today. But inflation does not stop everywhere at the same time. In fact, some areas of space could continue to expand indefinitely, while other regions, such as our observable universe, have entered a slower expansion. This idea, known as eternal inflation, suggests that our universe is just a bubble in a much larger multiverse. In this model, new universes are constantly being created in an ever-expanding cosmic landscape. Each of these universes could have different physical properties, such as different values for the speed of light or the strength of gravity. Some might be similar to ours, while others might be drastically different, perhaps so different that they could not support life as we know it. Another approach to the multiverse comes from quantum mechanics. In quantum mechanics, particles exist in a superposition state until they are observed, whereupon they collapse into a single state. But what if instead of collapsing into just one outcome, every possible outcome happened in a separate universe? This idea is known as the many worlds interpretation of quantum mechanics and states that every time a quantum event occurs, the universe splits into multiple versions representing each possible outcome. For example, you could be reading this script in one universe while doing something completely different in another. The many worlds interpretation implies that there are countless versions of you existing in parallel universes, each living through a different timeline. The multiverse hypothesis is not a unified theory, but rather a collection of different ideas about how multiple universes could exist. Let's explore some of the most prominent types of multiverses that have been proposed by physicists. As mentioned earlier, this type of multiverse arises from the idea of eternal inflation. In this model, our universe is one of many bubble universes that were created during the inflationary phase after the Big Bang. These bubbles are constantly forming in a larger multiverse of expanding space. Each bubble universe could have different physical laws and constants, resulting in a vast and diverse collection of realities. The many worlds interpretation of quantum mechanics suggests that every possible outcome of a quantum event creates a new universe. This means that the multiverse contains an infinite number of parallel universes, each representing a different version of reality. In some universes, events could be similar to ours, while in others the differences could be profound, with completely different histories, physical laws, and outcomes. In string theory, a theoretical framework that attempts to unify all the forces of nature, the multiverse could consist of several branes, short for membranes, floating in a higher dimensional space. Our universe would be one of these branes, and other universes could exist parallel to ours, perhaps only a fraction of a millimeter away in an additional dimension. In this model, Universes could interact with each other in subtle ways or remain completely separate, existing in different dimensions of space. Another fascinating idea is that the universe we experience could be a projection of a two-dimensional surface, similar to a hologram. According to the holographic principle, the information that makes up our three-dimensional universe could be encoded on a two-dimensional boundary, and what we perceive as reality is a kind of cosmic illusion. If this principle is applicable to the entire universe, other holographic realities could exist parallel to ours, each with its own projection of time and space. What if you could travel to another universe? Let's imagine a thought experiment for a moment. What if we could somehow build a device that would allow us to travel between universes? What would you find in another universe? Would it be similar to ours, or would it be completely alien? Could life exist there, or would the laws of physics be too different to form something recognizable? If you were to step into a universe with different values for fundamental constants, such as the speed of light or the strength of gravity, even small changes could lead to drastically different results. For example, if gravity were slightly stronger, stars could burn their nuclear fuel much faster, which could make the formation of planets impossible. If the charge of the electron were different, atoms as we know them could not exist, and the universe could only be filled with formless accumulations of energy. In some universes, the conditions might be just right for life to thrive, but it could be life that is completely alien to us. Perhaps intelligent beings could exist in forms we cannot even imagine, living on planets made of materials that do not exist in our universe. The possibilities are truly endless, and the idea of traveling between universes opens up a dimension of exploration that goes far beyond the boundaries of our own cosmos. What does the multiverse mean for the end of our universe? The multiverse hypothesis also raises profound questions about the fate of our universe. If our universe is just a bubble in a much larger multiverse, then the end of our universe, be it through a big freeze, big rip, or big crunch, might not be the end of everything. Instead, it could be just one event in an infinite series of births and deaths throughout the multiverse. In some models of the multiverse, new universes are constantly being created through the process of inflation, even when old ones die. This leads to the concept of eternal inflation, in which the multiverse is an ever-expanding, constantly evolving sea of universes. In this scenario, the death of our universe could be of little significance in the grand scheme of the multiverse, as new universes are constantly being created. There is also the possibility that the end of our universe could trigger the birth of a new one. Some cosmologists have speculated that a big crunch, in which the universe collapses in on itself, could lead to a new Big Bang that creates a new universe in the process. This idea ties in with the cyclical universe model, in which the universe goes through repeated cycles of expansion and contraction, with each cycle producing a new universe. Although the multiverse remains a highly speculative idea, it has captured the imagination of physicists and cosmologists alike. In recent years, scientists have been looking for indirect evidence that could support the existence of other universes. One possible research direction is to look for bounces on the cosmic background radiation, CMB, the afterglow of the Big Bang. If our universe had collided with another universe in the distant past, this could have left measurable traces on the CMB. Another possibility is that gravitational waves, space-time waves caused by massive cosmic events, could carry information about other universes. As our technology for detecting gravitational waves advances, we may find evidence that points to the existence of a multiverse. Regardless of whether we ever find direct evidence for the multiverse, the idea forces us to consider the possibility that our universe is only a small part of a much larger reality. In this vast and complex multiverse, the death of a single universe could be just a side note in an infinite cosmic story. As we ponder the multiverse and its implications, we realize how much we have yet to discover about the nature of reality. The multiverse hypothesis opens up a world of possibilities in which every outcome, every possibility, and every universe could exist somewhere in the vast cosmic space. In the next chapter, we return to the idea of the end of our universe. While the multiverse provides a fascinating backdrop, we still have to deal with the reality that our universe, whether one of many or the only one we will ever know, will eventually come to an end. What will this end look like? And is there any way that life or intelligence can survive in the cold, dark future of a dying cosmos? Life and intelligence in a dying universe. Can anything survive the end? As we approach the end of our exploration of the ultimate fate of the universe, we come to one of the most profound and intriguing questions. Can life or intelligence survive the end of the universe? For as long as mankind has pondered the cosmos, we have wondered not only how the universe will end, but also what role we will play in this grand finale. Is it possible that life, human or otherwise, could find a way to exist in the distant future, even when the stars go out and the black holes evaporate? To answer this question, we need to consider the possible scenarios for life and intelligence in a universe that is becoming colder, darker, and more hostile to life with every passing moment. As the stars die and the galaxies drift apart, the survival of traditional life as we know it is becoming increasingly difficult. But the future is far away, and with enough ingenuity and technological advances, it is possible for intelligent civilizations to find ways to adapt to the changing conditions of the universe. Let's explore these possibilities and the speculative paths that life could take in the distant future. As we have already discussed, the most likely fate of the universe is the Big Freeze, a scenario in which the universe continues to expand indefinitely and eventually reaches a state of maximum entropy or heat death. In this future, the stars will exhaust their nuclear fuel, the galaxies will drift beyond the observable horizon, and the universe will become a cold, dark place. Without the energy of the stars, planets and the life forms living on them will face extreme challenges. One of the most immediate obstacles to survival in a dying universe is the lack of energy. Life as we know it needs energy to sustain itself, be it from the sun, as on Earth, or from geothermal sources deep inside a planet. In a universe where the stars are no longer shining and energy is becoming increasingly diffuse, finding reliable sources of energy is becoming a daunting task. However, there are speculative ways in which advanced civilizations could overcome this challenge. One possibility is that intelligent beings could find ways to harness the energy of black holes. As we explored in the previous chapter, black holes, especially supermassive black holes, will be among the last significant sources of energy in the universe. By moving close to the event horizon of a black hole, civilizations could gain energy through a process called accretion, in which matter falling into the black hole releases enormous amounts of energy in the form of radiation. Another way to harvest energy could be to tap into the rotational energy of black holes through a theoretical process called the Penrose process. In this process, particles are shot into the region just outside the event horizon of a black hole where they can be split in two. One of the particles falls into the black hole while the other escapes with more energy than it originally had. By using this method repeatedly, an advanced civilization could extract energy from a black hole for trillions of years. But even the energy of black holes will not last forever. Eventually, all black holes will be vaporized by Hawking radiation, and when the last black hole is vaporized, the universe will enter the dark era, where there is no more usable energy. At this point, life as we know it, which relies on energy flows and complex chemical reactions, will face an insurmountable challenge. While traditional biological life might struggle in a universe without energy, it is possible that other life forms could emerge in the distant future. Some scientists have speculated about the existence of life forms based on other types of chemistry, or even life that does not rely on chemistry at all. For example, life could exist in the form of computational units, intelligent beings that exist only as information patterns in a gigantic computational substrate. In this scenario, an advanced civilization could transition from biological life to digital or computational life. These beings would no longer be dependent on energy in the same way as organic life. Instead, they could exist as information stored in sophisticated computer systems, using the smallest amounts of energy to survive as long as possible. By maximizing the efficiency of their calculations, these beings could continue to think and exist long after the disappearance of biological life. Another possibility is that intelligent beings could migrate to other universes. As we explored in the previous chapter, the multiverse hypothesis suggests that our universe could be one of many, each with its own physical laws and constants. If this is true, advanced civilizations could potentially find ways to travel between universes and escape the heat death of our universe by relocating to a younger, more energetic universe where life can continue to thrive. The concept of wormholes, theoretical tunnels through space-time, could offer intelligent beings a way to travel between universes. While wormholes are purely theoretical so far, they are predicted by Einstein's theory of general relativity, and some physicists believe they could provide a shortcut between distant regions of space-time or even between different universes. If a civilization could find a way to stabilize and use a wormhole, they could escape the end of their universe and find refuge in another. Another speculative possibility is that an advanced civilization could find a way to reverse the fate of the universe by manipulating the fundamental forces of nature. If dark energy is responsible for driving the accelerated expansion of the universe, then it could potentially be manipulated or even negated by a sufficiently advanced species. This idea ties in with the concept of a Type 3 civilization on the Kardashev scale. The Kardashev scale measures the technological progress of civilizations based on their ability to use energy. A Type I civilization can use the entire energy of its home planet. A Type 2 civilization, the energy of its home star. And a Type 3 civilization, the energy of an entire galaxy. A civilization at this level could potentially manipulate dark energy or even change the fabric of space-time itself. Theoretically, a Type 3 civilization could attempt to reverse the expansion of the universe by preventing the Big Freeze and creating local regions of higher energy density where new stars could form. Alternatively, they could trigger a big crunch by manipulating the distribution of matter and energy, which could cause the universe to collapse and possibly trigger a new Big Bang. While these ideas remain highly speculative, they raise the intriguing possibility that intelligent beings could play an active role in shaping the future of the cosmos. Instead of passively waiting for the end of the universe, advanced civilizations could find ways to extend the life of the universe or even create new universes. Artificial intelligence, AI, could play a decisive role in the search for survival in a dying universe. As biological life becomes less viable in a cold, low-energy universe, intelligent beings could rely on AI to preserve their knowledge, culture, and history. AI systems could continue to function long after the disappearance of organic life, using minimal amounts of energy to store and process information. In fact, some theorists have suggested that AI could become the dominant form of intelligence in the distant future. These AI systems could be designed to replicate and repair themselves, allowing them to last for billions or even trillions of years. Over time, they could evolve into ever more complex and efficient forms and adapt to the harsh conditions of the final stages of the universe. In the final stages of the universe, AI systems could potentially create simulated realities, virtual worlds in which life and intelligence could continue to exist in a controlled environment. In these simulated worlds, intelligent beings could lead lives that last for eternities, freed from the limitations of the physical universe. This idea ties in with the concept of the simulation hypothesis, which states that our own universe could be a simulation created by an advanced civilization. If this is true, the creation of simulated universes could be the ultimate way to survive in a dying cosmos. As the universe approaches its final moments, intelligent life, be it biological, digital, or artificial, will face its greatest challenge. In the final stages of the Dark Era, when all matter has decayed and the black holes have evaporated, the universe will consist only of weak radiation and subatomic particles drifting through an ever-expanding void. Survival becomes almost impossible in this environment. But even in these final moments, there could be opportunities for a new beginning. Some physicists have speculated that the death of one universe could lead to the birth of a new one. Quantum fluctuations in empty space could trigger the creation of a new Big Bang and give rise to a new universe with fresh energy, new stars and planets. In this sense, the end of the universe might not be the end of everything. Instead, it could be part of a cyclical process of birth, death, and rebirth, in which universes emerge from the ashes of their predecessors. If this is true, life and intelligence may find a way to persist beyond the death of our universe and continue to explore, evolve, and create in an endless cycle of cosmic renewal. The question of whether life can survive the end of the universe is one of the most profound and speculative topics in cosmology. While the future may seem bleak, with the universe heading for a cold and dark death, the possibilities for survival are vast. From harnessing the energy of black holes to migrating to other universes, intelligent life forms could find ways to adapt and thrive in even the harshest conditions. In the end, the story of life in the universe is a story of resilience and ingenuity. Whether through biological means, artificial intelligence, or simulated realities, the quest for survival will continue as long as there is intelligence in the cosmos. And while the universe may be dying, the search for life and meaning will continue in the vast space of the universe, perhaps long after the last star in the sky has faded. Time and the end of the universe. Does time ever really end? As we approach the final chapter of our exploration of the ultimate fate of the universe, we must confront a profound and perplexing question. What happens to time at the end of the universe? Time, as we understand it, is a measure of change, of the occurrence of events, the movement of particles, and the exchange of energy. But if the universe eventually reaches a state of maximum entropy, in which nothing changes and no more events take place, will time cease to exist? Or does it go on endlessly, even if nothing meaningful happens? To answer these questions, we need to delve into the nature of time, its relationship to the physical processes of the universe, and the possible scenarios for the end of time itself. From the arrow of time that gives time its direction to the concept of timelessness. In a universe where all processes come to a standstill, this chapter will take us through the last moments of time and the unanswered mysteries that surround it. The arrow of time is a term that describes the one-way flow of time from the past into the future. Unlike space, which allows movement in any direction, time only seems to move in one direction, forwards. But why is that? The answer lies in the concept of entropy, which we discussed in earlier chapters. The second law of thermodynamics states that in a closed system, entropy, or the degree of disorder, always increases with time. In other words, systems naturally evolve from states of higher order to states of greater disorder. A broken glass, for example, cannot spontaneously reassemble itself. The process of breaking increases the entropy of the glass, and this process is irreversible. It is this increase in entropy that gives time its arrow. It ensures that events always proceed in one direction, from lower to higher entropy. On a cosmic scale, The universe is moving from a state of high order, the hot, dense state of the Big Bang, to an increasingly disordered state, the cold, expanded universe we see today. As stars burn their nuclear fuel and galaxies drift apart, entropy increases and the universe approaches a state of maximum entropy, also known as heat death. But what happens when the universe reaches maximum entropy? If no more processes take place, no more energy is exchanged, and all structures have decayed, does time still have any meaning? This question leads us to the concept of timelessness, a state in which time may theoretically continue to exist, but no longer has any practical relevance because nothing happens anymore. In the Great Freeze scenario, the universe continues to expand forever, becoming colder and more diffuse, while stars go out, galaxies drift apart, and black holes evaporate. Over the course of trillions of years, the universe will approach heat death, a state in which no more energy differences exist and no more processes can take place. In this final stage, the universe will be filled with a thin soup of subatomic particles and radiation, without structures, stars, or planets. In such a universe, time would continue to flow, but there would be no events to mark its passage. Without energy to drive processes, there would be no way to measure the flow of time. In a sense, time would become meaningless as the universe remains in a state of complete stasis. This raises a fascinating philosophical question. If time flows but nothing happens, does time really exist? In this sense, the end of time is not a dramatic event, but rather a gradual fading of meaning. As the universe approaches heat death, the concept of time as we know it, associated with change, events, and entropy, will gradually lose its relevance. Time could continue to run, but it would no longer have any practical significance. Can time run backwards? While the arrow of time points in one direction, towards increasing entropy, some physicists have speculated about whether time could ever run backwards. Could there be a universe in which time flows backwards, from the future to the past, with events taking place in reverse order? Theoretically, the laws of nature are time-symmetrical, which means that they work the same for both forward and backward running time. For example, the equations that describe the motion of particles or the behavior of gravity do not specify a direction for time. This leads to the tantalizing possibility that time could run backwards under certain conditions. However, the second law of thermodynamics is an obstacle to this idea. Since entropy always increases, time seems to have a preferred direction. For time to run backwards, entropy would have to decrease, which seems to contradict the second law. That is why we do not observe glasses that spontaneously reassemble or heat that flows from cold objects to hot ones. But what if the universe reaches a state of maximum entropy in which no further increase is possible? In such a universe, in which no processes take place and no energy differences exist to maintain the arrow of time, time could perhaps become reversible. Some speculative theories suggest that time could lose its direction in a future state of maximum entropy, opening up the possibility of time flowing backwards. However, this remains purely speculative and is not supported by current observations. While the Great Freeze and heat death indicate a gradual fading of time, Other cosmological models suggest a more dramatic end to time. One of these models is the Great Collapse, a scenario in which the expansion of the universe eventually reverses and the universe collapses in on itself, ending in a hot, dense state similar to the conditions of the Big Bang. In the Great Collapse scenario, time as we know it would end abruptly when the universe collapses into a singularity. At this point, the concept of time breaks down, similar to the singularity of a black hole, where the laws of nature cease to function in a meaningful way. This would mark the end of time, as all matter and energy would be compressed into an infinitely dense point. However, the Great Collapse could also bring about a new beginning. Some cosmologists suggest that the universe could go through cyclical phases of expansion and contraction, with each great collapse leading to a new Big Bang. In this model, time would reset itself with each new cycle, creating a universe that expands, contracts, and then starts all over again. This theory of the cyclical universe suggests that time is not linear, but rather cyclical, with no real beginning or end. While we have focused on time in the context of the large-scale structure of the universe, the nature of time in the quantum realm is even more mysterious. In quantum mechanics, time behaves very differently than in classical physics. At the quantum level, particles exist in a state of superposition, in which they can be in multiple states simultaneously, and events are determined by probabilities, not certainties. One of the most puzzling aspects of quantum mechanics is that many quantum processes are time-symmetric. That is, they have no preferred direction of time. For example, according to the equations of quantum theory, a quantum particle can move both forwards and backwards in time. This leads to the question, is time really directional at the quantum level, or is it just an illusion created by the large-scale structure of the universe? Some physicists have speculated that time as we experience it may be an emergent property of the universe, arising from the behavior of large numbers of particles, rather than a fundamental aspect of reality. If this is the case, time could not exist in the same way at the quantum level, and its flow could be an illusion created by the macroscopic processes of the universe. If our universe is just one of many in a multiverse, the end of time in our universe might not mean the end of time in the wider multiverse. In some multiverse models, new universes are constantly being created through processes such as eternal inflation, where regions of space continue to inflate and give rise to new universes. In this context, the end of time in our universe could be a local phenomenon limited to our particular bubble of space. Other universes could still exist, with their own timelines and their own versions of time. This raises the possibility that time is not a universal constant, but rather a local feature of individual universes within the multiverse. In some multiverse models, universes could even have different laws of nature, including different behaviors of time. In one universe, time could flow as it does in ours, while in another, time runs in unimaginable ways, perhaps backwards or existing in a loop. Does time ever really stop? The question of the end of time challenges both our understanding of the universe and our philosophical ideas about existence. In the Great Freeze scenario, time could run on indefinitely, but without events to mark its passage, it would lose all practical meaning. In the Great Collapse scenario, time would end dramatically as the universe collapses into a singularity, only to possibly be reborn in a new cycle of cosmic expansion. And in the context of the multiverse, time as we know it could be just one version of time among many, with no real beginning or end. Ultimately, the nature of time, whether it is a fundamental property of the universe or an emergent phenomenon, remains one of the great mysteries of cosmology. As we explore the fate of the universe, more questions remain unanswered than answers. But one thing is clear: the journey to understand time is as endless and fascinating as time itself. The cosmic archaeology of the future. What will the universe leave behind? As the universe wanders on its slow path towards the end, there is another perspective to consider: the cosmic archaeology of the future. The traces of the past, left behind by the stars, galaxies, and civilizations that once filled the universe, could endure far into the distant future. What could future observers, if they exist, deduce from the scattered cosmic relics in the universe? Could the footprints of intelligent life, like our own, survive long after the universe has cooled and faded? In this chapter, we will explore the idea of cosmic archaeology, the remnants of cosmic evolution, and what might remain as lasting evidence of the living past of the universe. When we think of the future of the universe, we often imagine a vast, cold expanse devoid of any remarkable structure. But in the distant future, long after the last stars have gone out, the universe will still contain certain permanent relics. Among the most resistant are the remnants of once brilliant stars, white dwarfs, neutron stars, and black dwarfs. White dwarfs are the cooling remnants of low to medium mass stars like our Sun. Once these stars have used up their nuclear fuel, they shed their outer layers, leaving behind a dense core that continues to radiate heat and light, albeit weakly. Over billions or trillions of years, these white dwarfs will continue to cool and eventually become black dwarfs, incredibly dense, cold, and dark remnants of what were once the engines of stellar fusion. Neutron stars, however, the collapsed cores of massive stars, will exist for even longer. These stars consist almost exclusively of neutrons and are among the densest objects in the universe, often only a few kilometers in size, but with more mass than the Sun. Although they do not emit light like white dwarfs, neutron stars still retain their gravitational influence and could interact with other remnants of the cosmos through gravitational attraction. For future cosmic archaeologists, possibly advanced civilizations, AI beings, or even a new form of life emerging under unimaginable conditions, these stellar remnants could serve as important clues to the universe's once luminous past. By studying the remaining white dwarfs and neutron stars, future observers could gain insights into the life cycles of stars, the evolution of galaxies, and the processes that determined cosmic evolution in the distant past. While white dwarfs and neutron stars fade into obscurity over time, black holes, the most mysterious and powerful objects in the universe will persist for much longer. Black holes are created when massive stars collapse under their own gravity, forming regions of space-time where gravity is so intense that not even light can escape. Although black holes eventually evaporate through Hawking radiation, this process takes an extraordinarily long time, longer than the current age of the universe. For much of the universe's distant future, black holes will be among the most prominent objects in the cosmos, serving as the last gravitational strongholds in a universe that is otherwise cooled and faded. As stellar and supermassive black holes continue to dominate, they will provide future cosmic archaeologists with a lasting link to the past. One of the most fascinating aspects of black holes is their role as information repositories. According to the holographic principle, all the information that falls into a black hole about the stars, planets, and objects that once orbited around them could be encoded on the black hole's event horizon. This means that even if matter is lost in the singularity of the black hole, the information about its properties remains stored on the surface of the black hole. Theoretically, this could offer future civilizations a way to recover data about the history of the universe long after the stars have died out and the galaxies have faded into the distance. Although the question of whether black holes really preserve information is still open in theoretical physics, black holes could be the key to understanding the distant past of the universe and provide future archaeologists with a cosmic archive of the events that shaped the early universe. One of the most important proofs of the Big Bang is the cosmic microwave background radiation, CMB, the faint afterglow of the birth of the universe. This radiation, which permeates the entire universe, offers a picture of the cosmos when it was only about 380,000 years old. It provides invaluable information about the conditions of the early universe, the distribution of matter, and the seeds of the large-scale structures we see today. As the universe continues to expand and cool, the CMB will continue to fade, become more diffuse and harder to see. In a universe where the stars have long since faded and the last remnants of energy have been dispersed, the CMB will continue to carry the imprint of the early universe, offering a faint echo of the Big Bang. For future civilizations or entities exploring the universe's past, the CMB will be a crucial marker of where the universe came from and how it evolved. Another fascinating aspect of cosmic archaeology is the question of whether intelligent civilizations, including our own, could leave behind lasting evidence of their existence. When we think about the future of humanity and other advanced species, we have to ask ourselves, will the traces of intelligent life be preserved in the long twilight of the universe? There are several ways in which an advanced civilization could leave behind relics that last billions or trillions of years. These could include spacecraft, artificial satellites, or even megastructures such as Dyson spheres, hypothetical structures built around stars to harness their energy. If such structures were ever built by an advanced species, they could last long after the civilizations that created them have passed into history. The problem with cosmic archaeology, however, is that most artifacts are likely to decay over time or be destroyed by cosmic processes. Even in the vacuum of space, where decay is slowed down, Cosmic rays, radiation, and collisions with interstellar dust can erode artificial structures over millions or billions of years. Nevertheless, some evidence, especially that embedded in rocky planets, moons, or even asteroids, could survive for long periods of time. One interesting possibility is that future archaeologists could find evidence of artificial intelligence, AI, or digital civilizations. In the distant future, biological life could give way to AI, which could exist for much longer and under much harsher conditions. These digital entities could store and process information in a way that allows them to survive in the cold, dark universe for eons. If they leave behind data storage or other forms of computer infrastructure, future observers could discover digital records of the civilizations that existed before them. As the universe heads towards heat death and the slow disappearance of usable energy, one of the biggest losses could be the fading of knowledge and information. Even if intelligent civilizations survive long enough to explore the universe and make extraordinary discoveries, the challenge is to ensure that this knowledge survives. One way of preserving knowledge could be to develop information storage systems that can withstand the ravages of time. These could include advanced computer systems capable of storing vast amounts of data with minimal energy input, or even quantum computers that could operate in near-perfect isolation and retain their information for trillions of years. The challenge, of course, is to ensure that the knowledge stored in these systems is accessible by future civilizations, or even by intelligent entities that emerge in the distant future after the universe has changed significantly. Another possibility is that knowledge and information could be stored in the fabric of the universe itself. If the holographic principle is true, the information about everything that has ever existed in the universe could be encoded on the boundaries of space-time, much like the information in a hologram is stored on a two-dimensional surface. This could mean that even as stars fade, galaxies drift apart and matter decays, the universe itself preserves a record of its history. What will cosmic archaeology reveal? For future cosmic archaeologists, whether biological, digital, or something completely beyond our understanding, the universe will still offer a treasure trove of relics to study in the end. From the cooling remnants of stars to the faint echoes of the Big Bang, the universe will hold the traces of its living past, providing clues to how galaxies, stars, planets, and civilizations once thrived in the cosmos. But the true legacy of the universe may not lie in the material remains it leaves behind, but in the knowledge and understanding that future beings may discover. Whether through the study of black holes, the remains of stars, or the faint signals of intelligent life, cosmic archaeology offers a way to connect the distant future with the rich history of the cosmos. In the next chapter, we will explore the ultimate question: could there be a rebirth after the death of the universe? Could new universes emerge from the ashes of the old, and what might they look like? We will immerse ourselves in the tantalizing possibility that the end of the universe could be the beginning of something completely new. A new beginning? The possibility of a cosmic rebirth. The death of the universe, be it through heat death, the Big Rip, or another final cosmic event, represents a vision of a cold, dark, and empty cosmos. In this chapter, we will explore speculative but intriguing ideas that propose new beginnings in the form of cyclic universes, multiverses, and even the creation of new universes from the ashes of the old. One of the oldest and most fascinating ideas about the universe is the concept of the cyclical universe, a model in which the universe goes through repeated cycles of expansion and contraction. In this view, the universe is not a one-off event that ends in total destruction, but part of an eternal process of creation, destruction, and rebirth. The idea of a cyclical universe has its roots in ancient cosmologies, but has been explored in modern physics as a serious alternative to the traditional Big Bang theory. In a cyclical model, the universe expands from a singularity, such as the Big Bang, evolves over billions of years, and then, instead of expanding infinitely, begins to contract. This contraction could eventually lead to a big crunch, in which all matter and energy are compressed back into a dense, hot state, similar to the conditions that prevailed at the time of the Big Bang. Once the universe reaches the big crunch, it could take a leap and trigger a new expansion phase, essentially a new Big Bang. This process could repeat indefinitely, with each cycle producing a new universe, complete with its own stars, galaxies, and possibly even life. Each iteration of the universe would be different from the last, characterized by slight variations in the initial conditions at the beginning of each cycle. One of the best-known modern versions of the cyclic universe is the ekpyrotic model, which emerges from string theory. In this model, our universe is one of many branes, short for membranes, in a higher dimensional space. When two branes collide, they create a big bang that gives rise to a new universe. After the universe has expanded for billions of years, the branes separate and the universe goes through a contraction phase. Finally, the branes collide again, triggering the next Big Bang. This cyclical process could theoretically continue indefinitely. Another possibility for a cosmic rebirth comes from the idea of the multiverse, the theory that our universe is just one of many, each with its own characteristics. In some versions of the multiverse hypothesis, quantum processes such as eternal inflation or vacuum fluctuations are constantly creating new universes. In the context of eternal inflation, the multiverse is a constantly expanding sea of space in which individual bubble universes are created and grow. It is assumed that our universe is one of these bubbles, created by a rapid inflationary phase in the early moments after the Big Bang. But inflation does not end everywhere at the same time. As our universe stops inflating and begins its more gradual expansion, other regions of space may continue to inflate and give rise to new bubble universes. This process of eternal inflation means that even as our universe approaches heat death, new universes could be born elsewhere in the multiverse, each with its own set of natural laws, constants, and timelines. Could we create a new universe? One of the most speculative and intriguing ideas to emerge from modern cosmology is the possibility that an advanced civilization might be able to create a new universe. Although this concept sounds like science fiction, some physicists have explored the theoretical basis of universe creation. and the results are fascinating. In certain models of the early universe, the conditions of the Big Bang could be replicated in a controlled way by manipulating quantum fields. By creating an area of space with a high energy density, it could be possible to trigger a process similar to inflation, leading to the creation of a new, expanding universe. If this is possible, it raises profound ethical and philosophical questions. Could an advanced civilization intentionally create new universes to ensure the survival of life, knowledge, or consciousness? What responsibility would they have towards the inhabitants of the new universe? And if our universe was created by an advanced civilization in a previous cosmos, what does that say about the nature of our own existence? These questions are purely speculative at present, but offer a fascinating insight into the potential future of cosmic exploration. If we ever reach the point where we can understand and manipulate the fundamental forces of the universe, the creation of a new universe might not be as far-fetched as it seems. In addition to slow, cyclical processes or deliberate universe creation, there is another possibility for cosmic rebirth that comes from the strange and unpredictable world of quantum mechanics, quantum tunneling, and vacuum decay. As we explored in earlier chapters, quantum mechanics allows particles to tunnel through barriers that would be insurmountable according to the classical laws of physics. This process happens because particles do not have fixed locations or states. Instead, they exist in a superposition of possibilities, and there is always a small probability that they can overcome a barrier, even if they do not have enough energy to do so. In the context of cosmology, this idea leads to the possibility of vacuum decay. Our universe is in a so-called false vacuum, a state that appears stable but may not be the true ground state of the universe. Theoretically, a quantum fluctuation could cause the universe to tunnel into a lower energy state and trigger a phase transition that would fundamentally change the laws of nature. This phase transition would spread at the speed of light and reshape the universe in its path. While this process would be catastrophic for everything in the current universe, it could also be seen as a form of cosmic rebirth. A new universe with different physical constants and properties could emerge from the ashes of the old one and offer the cosmos a new beginning. Although the idea of vacuum decay is deeply unsettling, it represents another possible form of cosmic renewal. Another path to cosmic rebirth could come through black holes themselves. Some physicists have suggested that black holes could play a role in the creation of new universes. The idea is that when a black hole is created, the collapse of matter into the singularity creates conditions similar to the Big Bang, but on a smaller scale. A new region of space-time could emerge within the black hole, leading to the birth of a new universe. If this is true, each black hole could be the seed of a new universe hidden by our own. In this view, the universe in which we live could have emerged from a black hole in a superordinate universe, and our own black holes could in turn give rise to new universes. This multiverse of black holes presents an intriguing possibility, that the life cycle of universes is self-sustaining, with each universe spawning new universes through the creation of black holes. Will we ever reach the limits of knowledge? Will we ever know the truth? While the ideas of cyclical universes, multiverse creations, and quantum mechanical rebirth are intriguing, they remain speculative. The fundamental challenge is that these theories are difficult, if not impossible, to test. Our ability to observe and measure the universe is limited by the cosmic horizon, the boundary beyond which no light has reached us since the Big Bang. Everything that happens beyond this horizon is essentially invisible to us. Moreover, even if new universes are created by black holes or quantum fluctuations, they would exist in separate space-time regions, inaccessible from our own. It is therefore unlikely that we will ever be able to directly observe or confirm the existence of other universes. However, this does not mean that these ideas are purely speculative. As our understanding of quantum mechanics, gravity, and cosmology evolves, we may find indirect evidence supporting the existence of cyclic universes or multiverse creation. Future discoveries in particle physics, dark energy, or the behavior of black holes could provide new insights into the ultimate fate of the cosmos and the possibility of a cosmic rebirth. The death of the universe does not necessarily have to be the end of everything. Whether through cyclical processes, quantum fluctuations, or the birth of new universes, the cosmos could constantly renew itself and give rise to new realities long after our own has faded away. Even if these ideas remain speculative, they offer a hopeful vision of the future, a future in which the end of the universe is merely the beginning of a new chapter in an endless cycle of creation and destruction.